Hello, students. Hello, people. Welcome back to the channel. In today's class, I will be teaching units and measurement chapter. So it is a big chapter because there are quite a lot of topics in this one, and at the same time, it is a very important chapter. So whether the exam be Jee Mains, Jee Advanced, or Neet, definitely few questions are asked from this particular topic. One, two questions for sure. In fact, in 2020 NEET, they have asked four questions from this chapter. So it is an easy chapter, but scoring because you get a important easy but important because they ask in almost every exam. They ask questions from this chapter for sure. Okay, so let's get started without a further ado. Okay. So I discussed the name of the chapter is units and measurement. So the first term that we will understand in this one is physical quantity. So physical quantities are basically the quantities by means of which the laws of physics are described. Examples for physical quantities we have force, mass, distance, charge, temperature, etc. Okay, next let us understand measurement. So measurement is basically the process of determining how large or small any physical quantity is. Okay. Now to express any measurement, two things are required. To express a measured quantity, two things are required. One is magnitude, and the second one is unit. So magnitude will basically give us an idea about that how large or small the particular physical quantity is, whereas unit will let us know, unit will help us in understanding that what exactly is the physical quantity that has been measured. Yes sir. Like if you write 30 kg or 30 meter, both the magnitudes are same, but 30 kg means I'm talking about mass, a mass whose value is 30, no, 30 units, and 30 meter means I'm talking about length. So to represent any measured value, we need a magnitude and a unit. Magnitude will help us in understanding that how big or how small that particular physical quantity is, and unit will help us in understanding that which physical quantity we are talking about. Now let us have a look at different types of measurement systems. So there are three major type of measurement systems that we have. The first one is CGS system. Which is also known as centimeter, gram and second. So in CGS system of units, we measure length in centimeter, mass in gram, and time in seconds. The second system of units that we have is FPS system. FPS is foot, pound and second. In this system, length is measured in feet. Mass is measured in pounds, so its representation is lbs, and time is measured in seconds. The third type of system that we have is MKS system. MKS system stands for meter, kilogram, and second. So we have in MKS system, length is measured in meter, mass is measured in kilogram, and time is measured in second. Okay. Now, today in the world of globalization, where trade is happening between countries, and it happens that different countries follow different kinds of systems of units. So in that case, it might create confusion, or it might create a barrier in a proper trade. Yes or no? Means I have ordered something in meter, but in that particular country they measure the particular object, the length in feet. In that case, it can create a confusion, and a lot of conversion may be required. So to make things seamless and easier, we have something called SI units. SI units is International System of Units. So actually it stands for System International, uh, but for our understanding purpose we can call it as International System of Units. Okay, that is what it is intending to say. Okay. So basically it is internationally accepted system of units. So in SI units we measure length in meter, mass in kilogram, and time in second. Okay. Next we'll talk about physical quantities. So physical quantities in general are have been divided into two types. Okay. First one is fundamental quantities. And the second one is derived quantities. So fundamental quantities are also known as base quantities. So what basically fundamental quantities means, that these are the basic quantities. These are the quantities that we measure directly. They don't depend upon any other physical quantities. Okay, so generally they don't have any formula which is like the combination of other different physical quantities. So in a way we can say that they are independent of any other quantity. So there are 7 physical quantities which have been chosen as fundamental quantities. So let us see the 7 fundamental quantities first. So let me divide them in a box tables. Okay. So first we'll write the name of the base quantity or the fundamental quantity. It's SI unit. And then we have a symbol of the unit. Then we have dimension. So dimension is basically a unique representation that each of the fundamental quantities have been given. So we have several applications of dimensional analysis that we'll be seeing later. So the first base quantity is length. SI unit is meter. Unit symbol is small m, and its dimension is capital L. Second base quantity that we have is mass. SI unit of mass is kilogram. Unit symbol we have kg, and its dimensional representation is capital M. Third fundamental quantity that we have is time. SI unit is second. Symbol is S, and the dimensional representation is capital T. The fourth fundamental quantity that we have is temperature. SI unit for temperature is Kelvin. Symbol is capital K, and the dimensional formula is also capital K. Fifth one that we have is electric current. SI unit for electric current is ampere. Symbol is capital A, and the dimensional formula is capital A itself. Sixth one we have amount of substance. SI unit is mole. Dimensional unit symbol is MOL, and dimensional formula or the representation is also MOL. Seventh one and the last fundamental quantity that we have is luminous intensity. SI unit for luminous intensity is candela. Unit symbol is CD and the dimension is CD. Okay, so these are the 7 fundamental quantities that we have. So these are the basic quantities. All the other physical quantities that are there is found by the combination of these 7 fundamental physical quantities. Okay. So now we'll move on to the next part, and the next is derived quantities. So derived quantities are basically the physical quantities which are found by the combination of the fundamental quantities. So basically, apart from the 7 fundamental quantities, any other physical quantity that you can think of is the derived quantity. Okay. Examples we have speed, acceleration, force, energy, etc. Next, let us see dimensional formula for derived quantities. So that is another important aspect of this chapter, where we try to write a dimensional formula for several physical quantities. So dimensional formula for a derived quantity is basically the representation of the derived quantity as the power of dimensions of the base quantities. Okay. So that is like kind of definition for your dimensional formula. Okay. So now we'll see the dimensional formula for different derived quantities, how to write them. So for whichever derived quantity you need to write the dimensional formula, try to write it in the terms of the fundamental quantities. So as I was saying that whenever you need to write the dimensional formula for any derived quantity, just try to write the dimensional formula, try to write that particular derived quantity in terms of the base quantities or the fundamental quantities. So let us see the very first derived quantity, that is speed or velocity. So both speed and velocity has the same dimensional formula. So if we see the formula for speed, the formula for speed is distance by time. So distance is basically length, and time is time itself. So the dimensional formula for speed will get accordingly. So dimensional formula for speed is same as dimensional formula for length by time. So that is equal to L by T, or that becomes LT inverse. So now in standard form, now any general dimensional formula is represented in standard form. So in standard form, we need to include at least mass, length, and time. Since most of the physical quantities in mechanics can be represented by the combination of these, we try to represent any physical quantity in standard form, any dimensional formula in standard form. So here mass is not there in speed. In that case, the power of mass will be 0 and L to the power is 1. So that we don't need to write the power 1. We can leave it as it is. And T to the power minus 1. Okay. Same way if we see for a velocity. So velocity is nothing but displacement by time, right? Which in turn is same as your length by time. So if we try to find the dimensional formula for velocity, it will come out same. This will also be equal to L by T. or LT inverse, we can say. Okay. So the dimensional formula for speed in standard form is m to the power 0, L to the power 0, t to the power 0. Same way the dimensional formula for velocity in standard form will be m to the power 0, L t to the power minus 1. Okay. Now we'll move on to the second derived quantity, that is acceleration. Let us see about acceleration. So acceleration is nothing but velocity by time. So now velocity, as we know, it is displacement by time, or in a way we can say it is length by time. So it becomes length by time whole divided by time. So that is basically length by time square, right? So the dimensional formula for acceleration will be same as dimensional formula for length by time square. So that becomes L by t square. That can be written as LT minus 2. Okay, so in standard form the dimensional formula for acceleration is m0 L t minus 2. Okay. So it does not have any component of mass. Power of length is 1 and for t it is minus 2. Next fundamental quantity that will the next derived quantity that we will see is force. So force, we know the formula for force. Force is mass into acceleration. So again the idea is to represent it in terms of the base quantities. Now if there is any physical quantity whose dimensional formula is already known, then we don't need to again go in terms of the base quantities. The dimensional formula for force will be same as the dimensional formula for mass into acceleration. So the dimensional formula for force will get it as For mass, the dimensional representation is m, and for acceleration we have m to the power 0 L t to the power minus 2. So which upon simplification we get it as m L t minus 2. Okay. The next we'll see work. So again we have to go to the basics. The formula for work that we have is work is force into displacement. Okay, so now we can write it directly. The dimensional formula for work will be dimensional formula for force we already know, that is ml t minus 2, and displacement is nothing but length. So we'll simplify this. Upon simplification we'll get it as ml square t minus 2. The next fundamental quantity that we have is energy. So when we need to write the dimensional formula for energy, we can think of any energy formula that we know. We can use any energy formula and the dimensional formula that we are going to get will be same. Okay. So for example, for energy we can take potential energy. Potential energy formula is mgh. Okay. So now the dimensional formula for potential energy will become same as dimensional formula for mgh. Now m is mass. For mass we can write it as capital M. G is nothing but acceleration due to gravity. So acceleration due to gravity will have same dimension as that of acceleration. So it becomes Lt minus 2, and h is nothing but height or length in a way. So no need to write every time in standard form while simplification. At the end you can write upon simplification. So upon simplification what we'll get here is ml square t minus 2. Okay, same way we can also think of any other energy formula. So we can talk about kinetic energy. Now kinetic energy is half mv square. Okay, so the dimensional formula for kinetic energy we can write as, that will be same as dimensional formula for half mv square. Okay, now here one important thing we need to know is that mathematical numbers or values, they are dimensionless. So here half will not be considered for the dimensional formula, for writing the dimensional formula. We can ignore half and we can directly write for mass. For mass it is capital M, V is LT minus 1, so that whole square will be there. So again, upon simplification, this becomes M L square T minus 2. So we can see here that whether we use potential energy formula or kinetic energy formula, the dimensional formula that we are getting at the end is same. Okay. So in general, the dimensional formula for energy is M L square T minus 2. Okay. The dimensional formula for energy and work are same. Okay. The dimensional formula for energy is same as dimensional formula for work. You can see the unit is also same, and that is M L square T minus 2. Okay students, so there are a lot of things to be covered here. There are many physical quantities whose dimensional formula we should know. So I will be discussing those physical quantities later in this chapter. So probably in the next video. So stay tuned for that. And as I already told you, again, these set of videos are going to be very helpful for students who are preparing for Neet or JEE. So this video might be slow because I will be teaching in detail. I will be discussing several problems and several examples so that you understand better. If you find the video to be slow, you can always play the video at uh, 1.5x or 2x, and you can watch it if you feel that the pace of the video is slow. Okay. Okay students, thank you for watching. See you in the next one. Bye bye.